So that idea for going from logarithmic to exponential, exponential to logarithmic. So if we have an exponential equation, a to the x equals y, how do I transition that into a logarithmic equation? Log base a of y equals x, right? How do those numbers move around? We've been working on that for these, a couple days here. So seeing that I have an exponential equation, so I want to go from exponential to logarithmic, always keying in on my base. So my base here is 10. Because I'm going to write log base 10, and I know that log base 10 is not log base 10, but log base 10 is just log, common log. So log base 10 is just log of something equals something. All right, well, where does those somethings come from? So our exponent, remember our logarithm is an exponent. Logarithm equals an exponent. And then the 13 will then get sucked over to the other side, right? So as the x heads over to the right, the 13 comes over to the left. And look what we were able to accomplish, right? We were able to solve for x, right? X is now by itself. We could, throw that in our calculator and figure out what that's equal to. We're not going to, but right, we were able to rewrite the equation and get x by itself. Okay? Let's do it again. Who can do b for me? So Anthony, you missed something here, right? So the first thing I keyed in on was the base of my power was 10. Because I have base 10, I get to say log. That's the common log, is log base 10. Any other time, any other base needs to be stated. So if your function's log is base 2, then you should be saying log base 2. So yeah. So the one that's assumed is base 10. If it's anything but 10, we have to say what the base is. So log base 2 of 1.5 equals x. So yeah, you did a good job of getting the other two things flipped around. So log base 2 of 1.5 equals x, right? Okay. Flipping back the other way. Okay. So going from logarithmic to exponential. What I really like about this is that what do I key in on? I key in on the base, right? The base of the power or the base of the logarithm. So there's my base of my log. It's log base 5, so I'm going to write base 5 for my power. So 5 to the something equals something, right? So I need to fill in those somethings. Again, those things switch around. The logarithm is the exponent, right? A logarithm is an exponent, so the answer should be the exponent. So 5 to the negative 3 power equals x. Just like that, right? So x is solved for. We could type 5 to the negative 3 in our calculator, or we could figure it out in our heads. We should be able to do that. Okay. But you can see we have a value for x now. Okay. Can you still write 10 as a base? Yeah, I really don't want you to, Jarrett. Good question. When it's log base 10, I don't want you writing the 10. I need you, to not be doing that. In the same way, like, the index on a square root is a 2. I don't really want you writing a 2 on a square root. Right? We need to be really on board with that. When we say that, it's just log. We don't say log base 10. We write it as just log. We don't write it as log base 10. I don't know if you've ever heard that, like saying that math is like a universal language. Part of that is that we've all agreed to write things the same way, so that somebody doing this in France is just going to write log, and somebody that's doing this in like Mumbai is going to just write this as log. Like we all have used the same notation across the globe, so that it is more of a universal language. So these are conventions that were come up with a long time ago. We just need to keep following those conventions so we don't confuse things. So yeah, so I don't want you to write log base 10. I want you to know it's there. I don't want you to write it though. Thanks for asking that. All right, what about D? What you think, Mason? Mason must be AFK. Caleb, what you got for E?
E1/2 x.
Real close. Say that again. Just say it again. You're saying it wrong. You're saying it wrong, but you have the right numbers and stuff. You said E1/2 equals.
E to the exponent of 1/2.
All right, yeah. E to the 1/2 equals x. Great. E to the 1/2 equals x. Right, so Caleb recognized that we were base E, so brings that E down, and the x and the 0.5 switch places. Again, you could type that in your calculator, figure out what x is actually equal to. And we're not doing that right now, just more about can we get x by itself, right? We've released the x from the log, right? It's been unlogged. Okay, that's how we do that. Yeah, good, Jared. Good, Kyle. Okay. Anything A through D there you guys want to talk about before we start really applying that to these more complex problems? This right here, guys, I mean, this is what I've been on you guys about over the last couple of days, is this rewriting. You know, on the last two homeworks, the bottom sections have said, like, rewrite it, you know, to solve for x, you know, and then do blah, blah, blah after that. We're not going to say rewrite it anymore. It just says solve. You need to know that the key step to solving is rewriting. All right, we just saw that over and over again. It's all about just rewriting. Okay, so we're pulling that away, that little bit of scaffolding away. You need to be in on that. So like we saw at the end of yesterday's lesson or Tuesday's lesson, that we can do a little bit of normal solving, like what I think would be like pretty basic solving stuff before we go to that rewriting step. Okay, that you might need to isolate the power or the index, power or the log first before you can do the rewriting. Okay, that should be a pretty normal idea for solving that. You know, you guys have heard me talk about SADMEP and all that stuff, and we did this with the root equations. You know, we had to isolate the root before we could to get rid of it. Okay, so as I'm saying, isolate the power, isolate the log. You know, I got to be able to identify that. So here's my power, right? So what's over there with that power I need to worry about getting rid of, right? Or here's my log, and just, you know, one, recognizing that the 16 is in the log, it's part of the log, and so I can't pull the 16 out of it. Okay? You know, so for one, I have some work I need to do. I got something on that left side there with the power, whereas two, the log is by itself, so I don't need to do anything, right? So sometimes we might have to move something across the equal sign before we can rewrite. Yeah? And it should be really, you know, basic algebra stuff, right? It says multiply by -2, so I'm going to divide by -2. There shouldn't be anything too crazy going on here. So I get e to the 2x equals 100. Once your power is isolated, once your log is isolated, right, what do we do with it, right? We rewrite it. How do we get that x out of the exponent? We turn it into a logarithm, okay? It's rewriting. There's our step 2. So our key step in this process is that rewriting step. And I'm not going to say rewrite it as an exponential or rewrite as logarithmic. It's just rewrite. What form are you in? You got to get it to the other form. Okay? So we're in exponential, but it's still, what do I focus on? Focus on the base. So this is log base, or this is base E. So I'm going to become log base E, which we don't write. We say instead natural log. So base E means natural log of some number equals some number. And where do those things come from, right? Those are those things that always flip inside. So the 100 pops over to the left side, and the 2x pops down there to the right side. But at this point, guys, you should be asking yourself, did I help myself in doing that? Right? Did rewriting it make this easier? And so what I'm asking you guys to recognize is that look where the x is now. It's not stuck up here in the exponent spot where I'm not sure what to do with it. Now it's down here, and we're used to seeing the x in that main level of the math, right? It's been freed up from this thing here. So I guess the main thing you could do that would be a mistake, would be to switch these numbers around. And so if you look at it like this, you're like, did I accomplish anything? Well, now the x is just stuck in the log. Like, what was the point, right? So kind of recognizing that it didn't help, like, oh, okay, I must have made a mistake. So that's what I'm trying to get at. So there's our rewriting step. Okay. Next thing I want you guys to try to wrap your heads around, which is a little bit trickier with these problems here, is that this right here is a number, but it's not 100. Right? The natural log of 100 means e to what power equals 100. It really has nothing to do with 100. This is going to be some gross decimal. I don't want to deal with that gross decimal right now because I still have work to do because I'm not actually done solving. So there might be a step 3 sometimes. Okay? Because x is not by itself. But both step 1 and step 3, guys, they should be really simple algebra 1, pre-algebra things. How do I get x by itself? Right? Oh, I'm going to divide by 2. Okay, so there really shouldn't be anything too crazy things. It's not like you're going to be like doing the quadratic formula or anything like that. Okay? But what I want you guys to see is that I don't want to deal with this messy number right now. I don't want to try to write it down. Okay? I just want to leave this and be okay that that's just a number. Okay? Sometimes that's kind of hard to wrap your brain around. Like, this is just some number. It's just some messy number, and I'm going to divide it by 2. Okay? Because that'll get me x by itself. So sometimes it's just hard to make your brain be okay with that. At this point of the problem, I really like to have the x on the left side just because that's purely my thing. You guys don't need to do this if you don't want to. Okay, so the natural log of 100 divided by 2. And Aiden asked a question kind of like this yesterday or Tuesday. And I guess I just make sure you guys understand that okay, that does not equal the natural log of 50. Okay, this doesn't work. I'll show you here in a minute. Okay, that natural log is, again, some crazy number. E to some power equals 100. Okay, it has nothing to do with 100. So dividing it by 2 does not give us anything like about 50. So there's our exact answer, the natural log of 100 divided by 2. We're going to go to our calculator. So really, when you guys are thinking about using your calculator, it should be the very last thing you do on any of these problems is touch your calculator. Okay? So now let's go and look at the natural log of 100 divided by 2. You guys should all be doing this. Just get that little bit of muscle memory down for yourself. Where do I find these buttons? Okay. If it's on your calculator, if it's in the app you're using, you just need to be able to access those quickly. So on test day, you're not like, where's my natural log button again? I can't find it. Okay. So either you have like a TI 30 something, you got a TI 80 something, you've got a good scientific calculator app. You should not be using the one that came with your phone. Those suck. So there it is, 2.033. 2.303. Here's the natural log of 50. That did not work, right? You can see very clearly that those are different numbers. Would not have been okay to do that. Okay? So 2.303. So this is what I wanted to see from you guys. Here's your exact answer. And here's your approximate answer. All right. And of course, all the work to get there, but like far as answers go, I want to see your exact answer and your approximate answer. Anything there, just sending neurons into the stratosphere? You good, Anthony? How you doing, June? All right. Okay, let's look at 2. 2 is a little simpler because we don't have to do step 1, and the log is isolated. So again, just really noticing that the parentheses are holding all of that stuff in the log. It would be so wrong to try to subtract 16. Okay, the 16 is something's happening to the 16, so it's not a 16. Okay. So we don't have to do step 1. It means we go straight to step 2. When we do step 2, we're always looking for that base, right? So this is base 3. So 3 to the something equals something, right? That's what this means. So how do those things move around, right? So 4 will become, remember, the log is an exponent, so the 4 is the exponent, and the argument is what heads over to the other side. So 3 to the 4th equals x plus 16. I'm just stopping. Did I do something that was helpful, right? The x was stuck in the log. Now look where the x is. It's been freed from the log, right? I just got to get rid of that 16, but I don't get rid of that 16. That's easy, right? So like seeing how that's helped us make the problem, simpler to figure out. So again, there's that rewriting step. Okay. Again, that's the key step to all these processes, is getting it out of that form that it's in into a different form. Now, last time I told you guys to sit on your calculator, okay, for a reason, because the natural log of 100 was going to be a messy number, right? What power of e is 100? What's up? But 3 to the 4th, and I don't even really need a calculator to figure out what 3 to the 4th is. 3 times 3 times 3 times 3, that's just 81. That's not a messy number. Okay, if you need a calculator to figure out what 3 to the 4th is, go for it, but it's not a messy number. So I'm saying, let's go ahead and simplify that, right? 3 to the 4th is just 81, so let's just call it 81, right? Versus some really gross decimal. So just being a little bit contextual here, guys, it's okay to do this because this is a nice number versus I don't want to do it yet on the other one because that's a gross number. So just trying to stay away from those decimals as long as we can, so that we're not tempted to round during the middle of the problem. So that's really what I'm trying to get you guys to avoid, is any rounding during the middle of a problem, because that will just make things go bad. And there we get a nice, cute little answer, 65, right? It was easy. We don't have an exact answer and an approximate answer. We just have an answer. So this one turned out pretty neat. Pretty clean, I should say. Anything there on 2? How you doing, brother?
How do you know if it's going to be natural or approximate?
I mean, a lot of that's just, me having to deal with numbers all the time, but if I just think about what's 3 times 3 times 3 times 3, that's just a number, right? It's not going to be a messy number. It might be a big number, but it's not a messy number. When I say messy, I'm really trying to avoid long decimals, right? The natural log of 100 means e, which itself is a decimal, to what power is 100. I know that's not going to be a pretty number. Or if I'm not sure, I could see what the natural log of 100 is, and I notice that it's not a pretty number. But pretty much most logs aren't going to be pretty. Most logs are going to be some sort of exponent, some number, just some exponent, which is usually, from what we've seen, and most of them are messy. So, and we'll see that here on the next one. The next time it'll be log, it's going to be a messy one again. And next time we go and solve a log, it's going to turn out to be neat again. So, which isn't always the case, but kind of see a pattern here. So I think it's just, a lot of it's just playing on my experience, but so. Good question. Brandon was just asking, how did I know that one was going to be neat versus the other one not going to be neat? So, anything else there, guys? All right. So again, the idea of step 1: do I need to isolate? Right. So where is my power? Where is my log? Identifying that. So this is the power, right? Here's the number being raised to an exponent. So all of that is the power. So is there something I need to get rid of? Or over here, here's the log, right? And looking at those parentheses, there's the log. So is there something I need to get rid of? Again, at this point, that stuff should be really basic level algebra. I've got a minus 2.75. I've got a minus 3. We should know how to get rid of those. We've done that hundreds of times. Okay. Add 2.75 to both sides. Over here on 4, I'm going to add 3 to both sides, right? Nothing earth-shattering going on here. You know, watch your handwriting, that stays looking like an exponent. So if you need to write larger so that you're able to write those other things smaller, then do that. We have 1.5 equals, or 1.5 to the x plus 4 equals 8.75. And we're at this, this point really where we're at that, we have an exponential equation, right? That some number to some power equals some other number, right? This is where we are. So that means we need to get ourselves here. So what you got, Aiden? How would I rewrite that? Mm-hmm. Look up at number 1 or look up at number 2. On the top. Or I'm sorry, A and B. Yeah. You guys would be so disappointed what's going on here. Check in.
You want me to divide the 1.5 into 8? Or wait, that's the big. Okay. Log 1.5.
So Caleb just asked, like, should we divide, right? Really common thought. And then you very quickly said, wait, that's the base. So you started changing it, right? So yeah, definitely a misconception we got to really fight. Okay? That's the base of the power. I can't divide it away, but instead what are you saying, Caleb?
Log base 1.5.
Yeah, log base 1.5, right? So that's definitely, it's a good mistake to make, Caleb, so we can talk about that. Like, that's such a common thought, right? And then, sorry, what was next? 8.75. Yeah. So, this really is the tricky part of these guys, like, is seeing that, right? Do you see that as a problem that needs to be rewritten? That's what I've been trying to get your brains trained to do over the last couple of days, is see those as things that need to be rewritten, not solved in any other way that we know, right? The only way we know to get that x out of there is by rewriting the whole thing. Okay? Does that match what you're thinking, Braylon? Okay. So the next little brain train, right? This means 1.5 to what power is 8.75? Just kind of realizing that's not going to be a good thing. Like, it's not going to be a pretty number. It's not going to be like 2 or something like that. Okay? So just being okay, like, I'm just going to leave that. I'm going to walk away from that right now. And I'm just going to keep myself focused over here with the x, right? I still need to get that x by itself. So just trying to be okay with that messy number over there. Okay? So we're going to bring that 4 over to the left side. And actually, I'm going to bring it over to the right side because at this point, now that x is by itself, I like to rewrite the problem so everything's on the other side. So. And if you don't want to do this, you certainly don't need to, as far as like flipping everything around. And again, just that we can't do that. All right, we can't take the 4 away from that because that's not actually a 8.75. It's something that's happening to 8.75 that won't be anything like 8.75 anymore. So we can't take 4 away from it. Okay, so we can say we want to take this gross number and subtract 4 from it, but we can't do that yet. Okay, we just say we want to do it. Okay, so you're just trying to get your brain to be okay with that. All right, we're almost done. We just need to be able to do this. How do we figure out what this is? We know it's going to be a gross number. But how do we figure out what that gross number is? How do we plug in our calculator? If I hit the log button, though, what's the base on the log button?
I don't know why, but whenever I try to do that with log times 5, figure that out.
So how do we evaluate this, guys? How do we evaluate that, Brian? How do we evaluate that, Tian?
The iteration thing, log times.
What's that called? There you go, Kyla. Speak that loudly, Kyle. You guys are always whispering in my ear. I don't like it. Yeah, change the base. Okay. There you go. Yep. Remember the big thing we learned Tuesday, core concept is what we called it. How do we figure out these problems that we couldn't figure out before? We use change of base. Okay? That we rewrite log of any base as a ratio of log, common log, or a ratio of natural log. And then again, my habit is always just use common log. That, the base of the logarithm is the base of that fraction. So that's the one that goes down there. So log of 1.5 would go on the bottom, and the log of 8.75 would go on the top. Then minus 4. Okay? And I can type that into the calculator just like that, as long as I'm good about closing those parentheses, just like we talked about on Tuesday. As long as you're good about closing those parentheses, you type it just like you would read it, and you'll be fine. Okay? So just be good about closing those parentheses. So again, you guys should all be practicing this just to get used to doing it. Okay? The more times you do it, the easier it's going to be. Silly as that seems. So again, closing those parentheses, making sure, all right? Then when I go and I look over at the left side, it should look like I wrote it. You can always check that, like, is the calculator doing what I'm asking it to? Okay. That's exactly what I wrote, so I should be pretty confident about my answer. So 1.3495, well, that 5 is going to round the 9 up, which would then subsequently round the 4 up. So 1.350. And you would need the 0 since we did round it. So there's our exact answer versus our approximate answer, right? I guess really this part. That's a pretty intense problem. I think as far as logarithm stuff, that's by far the hardest problem we've done together. So pretty intense problem. But, change of base. This needs to be in your wheelhouse, guys, right? Because most of these logs are not going to be base 10. They're not going to be base E. They're going to be something else. So. How you doing, Sophia? How you doing, Jubal? Yeah. Yeah, just check it in if you want. All right, this one's be pretty nice to us. Kind of like number 2 was. So we already saw that we were going to get rid of the 3 first. Okay. So our log is isolated. So once we isolate the log, that's our step 2. Where do we go next? 10 base, okay. So Tion's saying we should see there's a 10 there. Base 10. 10 to the what equals what, Tion? Oop, I wrote something wrong here. Got my x there. Hmm. 10 to the what equals what? I should go here. I should go there. 10 to the 4 equals what? 25x, right on. So 10 to the 4 equals 25x. Okay. So did we help ourselves, right? We freed the x from the log. So over there on the main part of the math now. It's not quite alone, but we sure as heck know how to get it alone. And in kind of the same way, Braylon, looking at that 10 to the 4th, right? Is 10 to the 4th going to be a messy number? No, right? It's a big number, but it's not a messy number, right? So it's 1 with 4 zeros after it, so it's just 10,000. Right? So then divide by 25, right? 10,000 divided by 25, that's pretty easy. X equals 400, I think. You guys certainly could check your answers. We're not asking you to because the checks are kind of intense, time intense and just like math skill intense. So we're not asking you guys to check. So I think unfortunately you do lose a little bit of the, like, did I get the right thing? Like, it's hard to know, especially with like something like 2.303. So unfortunately we are pulling that away just because we don't want you guys to like really be bogged down in how to check. The process of checking hasn't changed. You plug your answer in. You simplify down. It's just that the math that happens during this check is much more intense than the math we were doing in the last section. So we're not asking you guys to do that. So it's good in that way, but it's also bad because you don't know if you got the right answer before you walk away. So, all right, anything you guys want to cover here before we flip to the other side and see what happens? Silence is golden. Okay. So we just did this last unit, right? Dealing with these formulas right here. They should be very familiar to you. What we asked you guys in the moment, come test time, was to be able to look at the problem and say, hey, here's a word or a phrase I see. What formula should that lead me to using? Okay. So we're still expecting you guys to be able to do that. And then once you know what formula you're supposed to use, like what's P, what's R, what's N, what's T, like what are those things? Okay. So how do I pull those things out? So what you're going to notice though that's different about these questions, like why are we doing these questions again? Well, the question's different. How long? How many years? That was information I was giving you previously, right? But now that's the question. T is what, right? T is what? Well, where is T every single time? Right? T is the exponent. How do I figure out what the exponent is? Logarithms, right? So logarithms are what allow us to solve these questions that are very useful questions. If you have $1,200 in this account and you are trying to save $3,000, like how long will it take for you to get that $3,000? If you're looking at a population of animals and there's how many there are right now, and that there's like a critical amount, like if it goes below this, then the population won't recover. And that's something that's, out in the news right now. Like, how many years till we have not enough that they can then rebound? Like, because there is a certain amount of animals. If there's too few, then they can't regrow the population. Like, how long until we have that? Like, those are things we would want to know. Right? It's not going to help you pay your bills, but it's, there are people that do this for their living. Like, they work with money or they work with animals and things like that. Or if you're at all interested in like designing sound stuff, like the decibel scale is a logarithmic scale. Or if you're at all interested in like geology, like the Richter scale is a logarithmic scale. Like all this stuff with earthquakes that's been happening recently, that's a logarithmic scale. Okay? Money, populations, all these people use this math as part of their understanding of what's going on in their life, so, or their job. And certainly, I have plenty of jobs that don't do this stuff, but there are also lots that do. So this is a very, very applicable type of math. So it's important you guys to see some of that. So that's why we're looking at this. Okay? So reading this problem, what's the phrase, the word that tells us which of these three equations to use? What phrase or word in here says, hey, use this equation? What should you guys be keying in on?
Compound.
Compounding, what's that? So if you're keying in on that, Jarrett, which formula is that saying to go look at?
The middle one, I think.
Middle one, yeah. Does that sound right to you guys, that compounded should be the middle one? Sam saying yes, Kyla saying yes. Okay. And this word right here, what variable did that keep getting assigned to semi-annually and yearly and monthly and daily? Those words, they kept getting assigned to a certain letter. That was n, right? And so if I can recognize semi-annually as being an n value, then which one has n in it? Well, there's only one that has n in it, right? So yeah, the compounded, or recognizing one of those n value words, can be very helpful in saying that's the middle formula, not the other two. Right? Yeah, right on. So we know n is 2, semi-annually meant twice a year. If we're going to find time, that means we need to know everything else. So I know n is now. That means I need to know what r is, and I need to know what p is, and I need to know what a is. So we know n. We also need to know r, a, and p. So where do we find those in the problem? What's r, what's a, what's p? R 2.6 means the rate, right, Jarrett? What do we do with those rates as we go to use them? R is 2.6, but we don't use 2.6. What do we do instead, Jarrett? No, you're gonna get ahead of yourself. Yeah, there you go, Kyla. All right, we need to change it to a decimal. 2.6% as a decimal is 0.026, or 2.6 out of 100. 0.026. And we have A and P. So remembering what those letters stood for, P was the principal. That's the amount we put in, or the amount we invested. A was the amount that came out, the amount at the end. So what's A, what's P? P equals 1,200, yep. So we put 1,200 in, that's our principal. And yeah, there's only one other number left, right? So when you're doing money problems like this, that compound interest problems, the principal should always be smaller than the amount. So if you need like a little hint in a problem like this, A would always be bigger than P. You only have two numbers that could be. They're both the only two money numbers, so they're easy to mix up. But A is always the bigger one compared to P. So because you're going to end up with more money than you started with because you're saving money. So if you're not sure which is which, the good rule of thumb is that A will always be bigger. So we have our four values. We need to go plug those in. So 3,000 equals 1200 times 1 plus 0.026 divided by 2. Now this says to the nt, so that's 2 times t, so 2t. So there's everything plugged in. Then we can see that our only thing we don't know is t, right? That's the thing we're trying to find, which is what we need to have in there. Everything else needs to be a number, right? Visually, if you need this, there's multiplication there. Sometimes it gets a little sticky if we don't remember that. And then there's multiplication right there. So if you need those dots to help you remember that there's multiplication there, then you do that for yourself. Okay? I don't typically do that for myself. If you need it, go for it. Okay? First thing we want to do is simplify this down a little bit before we try to solve it. So all this stuff inside of the parentheses, right? Think about PEMDAS will tell us to go inside the parentheses first. We need to deal with that right now. What is 1 plus 0.026 divided by 2? Okay? Nothing else is going to change yet. So 3,000 equals 1,200 times some number to the 2t. So 1 plus 0.026 divided by 2, 1.013. Do not round, do not round, do not round. Grab all those numbers. 1.013. Okay. And now we're solving. Okay. But I really need you guys to make sure your thinking is not okay. You are not allowed to multiply those numbers. Okay? Quite clearly, 5 times 2 cubed does not equal 10 cubed. 5 times 8 does not equal 1,000. Okay? You cannot multiply those numbers. That is not a 1.013. That is 1.013 to the sum power. I am not allowed to multiply those numbers. Okay? We just did a problem like this over here. First thing we got to do is get rid of that thing, right? We got to isolate our power. I didn't take the 2 times the e, right? I got rid of the 2. So, all right. Yep, we're going to divide both sides by 1,200. So I just need to make sure you guys, that's by far one of the most common mistakes. People are like, oh, I'm going to simplify that, smush those together, and then you're done. No, there's no way you can recover from that. So instead, we're going to get rid of the number. I believe that's 2.5 after having done this twice already. Okay, so here's our exponential problem, right? Some number to some power equals some other number. I've seen a lot of students over the years get confused at this point because this problem is backwards from every problem we've done so far. Literally every problem we've done so far before this one has been written the other way. So if you are looking at that and you have no idea what to do, and it helps you to do this instead, then do that. Okay? The numbers don't care what side they're on, but if you care, then move them. Okay? For me, I know that if this is exponential, I want to rewrite it as a logarithmic. The main thing I have to worry about is the base. The base is still the base, no matter what side of the equation it's on, there's the base. So there's the base of my log. And then I get to decide where I want to write it. I want to write it on the left, because that's what I've been doing. So log base, sorry, that's crappy handwriting. Should probably write bigger. Log base 1.013 of some number equals some number. Well, where do those come from? Those are my flip-floppers. All right. 2.5. Well, it's going to jump to the same side as the 1.03, which means it's going to be over here. And then the 2t is going to jump to the other side, which means it's going to be over there. Right? Remember, our goal is always get that t or the x, whatever it is, out of the exponent, right? To free it up. Did I free the t up? And there it is, right? It's down in the main level again. So we're just kind of thinking that we've met our goal of doing that. So, okay. But if you need to do this, guys, then do it. This takes you 3 seconds to rewrite the problem, and then all of a sudden it's doable. Okay, just take that time for yourself. Okay, whichever way it needs to be rewritten, right? And it's still just, that left side, log base blah blah blah. It's going to be some gross number, so I don't want to deal with it right now. I just want to make sure I can finish the problem, which means divide by 2. Okay. So this one in the end, it turns out to be pretty similar to problem 3 on the other side, as far as just kind of like the messiness of it. Because this right here still needs to be rewritten with that change of base stuff. So if you look at the steps that we did on number 3 and you compare them to the steps we're doing here, they're pretty much exactly the same. And we need to rewrite that using change of base. And this by far is, just like on the other side, that was the hardest one. This by far is the hardest problem on this. Those 2 problems are the hardest ones on this paper. So what I'm going to do when I write that is write it like that, where I'm putting it just, I want to divide by 2. What I'm trying to avoid by doing it that way is, if I had written it as like over 2, I don't think there's too many of you guys that are comfortable with like a fraction on top of a fraction. Like, it's not something we normally look at. So I'm just choosing to write it a different way, as I want to take that fraction and I want to divide it by something. Okay, I'm just going to write it to the side of it instead. And again, as long as I'm good about closing my parentheses here, I can write it just like I would say it. Log of 2.5 divided by log of 1.013 divided by 2. I can say it and I can type it just that same way. And it'll spit out my answer for me. So there's our exact answer. Messy answer. All right. What's the approximate answer? Okay. Let's see what that is. Okay, so log of 2.5 divided by log of 1.13 divided by 2. Make sure all my parentheses are in the right spot. You can see how it writes it over there on the left. That's what I showed you guys just a second ago, the fraction on a fraction. Not super happy about that, but that's what it was. Okay, and then there's our answer, 35.5. I told you guys to round to the 10th, so 35.5. Says it up here, round to the 10th. Okay, so 35.5 years. So you can see that, putting money into a bank account is not a good way to make money. It took it 35 years to go from 1,200 to 3,000. Okay. Banks are nice places to keep money. They're definitely not places to make money. So obviously we're out of time. I'm going to try to go ahead and finish this video here in a minute, and when I post it. But so if you guys want to watch it at the end of it when you're trying this later, you certainly can. All right, let's see if we can. If you want to do these last couple examples here, so because they're considered local delicacy, the population of blue-tongued skinks is declining. There's an important word right there, by 11% per year. About 2,000 skinks in Lawrence now. How many years until only 500 left? So declining would tell me that I want to use this formula here. So I'm bring that down real quick. Oops. So y equals a times 1 minus r to the t. So just that idea that we want to find t. So that means we need to know everything else. So we're going to need to know the rate, and we're going to need to know the initial population, and we're going to need to know our final population. And so with the declining problem, the initial population should be bigger than the final population. So we look at this and say that the 2,000 must be our initial, and you can see that that's what it says now, right? And then the final population, when is there going to be 500? That would be our final, and then of course R being the 11%. So 500. Oops. Equals that 2,000 that we have now times 1 minus, and that 11% would be 0.11 all to the t power. So there's our equation that we need to solve. And pretty similar to the last one. First thing I want to go ahead and do is just simplify what's inside the parentheses there. So 1 minus 0.11 turns out that's 0.99, or sorry, 0.89. So 500 is 2,000 times 0.89 all to the t power. And just like we talked about on the last problem, that you are not allowed to multiply these. That's definitely a very common mistake. What instead we need to do is get rid of the 2,000, not try to multiply it again. So, and 500 is a fourth of 2,000, so that'd be just 0.25. Okay, so we're at that point where we have an exponential equation. Again, if you really feel like that it's easier for you to solve when the power's on the left side, then you go for it. You rewrite it for yourself. I don't really feel the need to do that. What I want to focus on is what's the base of my power, which is the 0.89. So that means I'm going to be at log base 0.89 of equals something, and this is where the 2.5 would come over to the side of the log. So it'd be log of 0.25, and then the t will get released down. Right? We see that we've actually solved for t. So there's our exact answer of log base 0.89 divided by of 0.25. And so, but we do want to use our change of base. To figure out this. So t is going to equal log of something over log of something, and that base always goes to the bottom. So 0.89 at the bottom, the 0.25 will go to the top. And so let's check what that is. Divided by log. So 11.89, so 11.9 actually goes around to the 10th, so 11.9. This is time. We're talking about decreasing by a certain amount per year. 11.9 years. So in about 12 years, there'd be maybe a critical number of skinks, and we couldn't eat them anymore, or else the population would never recover. So, all right, last one, radioactive decay, so carbon dating type thing. With this, we have given you a specific formula for the carbon dating. So A, which would be our final amount, is equal to some beginning amount times E, and then we have this crazy big, tiny decimal, negative 0.0043 t. Right, so there's our rate and our time. Again, the A represents like how much you have after a certain amount of time. And then the P would represent like that initial amount, just like with the principal and the amount on the compound interest formula we did earlier. So if the initial amount P of the radium was 800, so they're telling us that this P is 800, and then the current amount A, so A is 24. How old is the sample to the nearest year, right? So how old? Well, that's a time question, right? How much time has passed? So t equals question mark, right? So there's our job. This is solve for t. So we can see that we know everything but t, right? That we know the a value, we know the p value. Remember, e is just a number; it's not a variable. We know this, that r essentially, and then what t is. So go ahead and plug all that stuff in. So 24 equals 800 times e to the negative. So watch that negative. That's really easy forgotten. T. So our job is to solve for t, and just like we've seen so many times already, is that 800 and the e you can't multiply. Our job is to get rid of the 800, not try to multiply it in. So get rid of that coefficient first. So 24 divided by 800, let's see what that is. 0.03, all right. And make sure you don't lose that negative there. Make sure you got no zeros. And then, all right, we're at that point we want to rewrite this again. If rewriting this becomes simpler for you by pushing everything to one side versus the other, make sure you do that for yourself. For me, I want to look at that base. That's log base e, which I know is natural log. So the natural log of something equals something. That answer is always my argument, so that 0.03 I'm going to put there, and then my exponent should release down to the main level of the math, so it'll be negative 0.00043t. So I can see the t is almost by itself. I just need to finish this up by dividing by negative 0.00043. Divide by negative 0.00043. So really watch that, all those zeros, that negative. I can't tell you how many times I've seen people just drop that negative off and it makes everything go weird. So I really just want to type this into the calculator just like it says, the natural log of 0.03 divided by negative 0.00043. We're talking about carbon dating that this, or this radioactive decay is usually many thousands of years, if not many more. So seeing a number like this, and I think it said round to the nearest year, so that would be 8155, since that 7 would round up to 4, so 8155. There we go. Not too shabby. Hope you guys have a wonderful weekend. Be good.